So back to the fun of things. We are going to do, we don't want to intermix PCA with factor analysis. Actually, there's a question at the break that I really appreciate. How you know it's a PCA-based method is if in your output somewhere it says eigenvalues. Eigenvalues are your diagnostic tool. If it says eigenvalues and someone says, look at my factor analysis, you can be like, yeah, that's principal. Right? I haven't described yet why I hate that. I will shortly. Actually, no, I'll say it now. One of the things about PCA, to put in your input for it is a covariance matrix, right? Or a correlation matrix. What happens to your correlations, your covariances, if you have missing data? Oh, not good, right? Bias. Missing data problems really affect principal components analysis. In ML, EFA, or CFA, the missing data don't affect you as much if so long as they're missing at random. It's a little bit looser relaxation of assumption. So you're able to get things a little bit better, I think, from it. So, okay. So here's a terrible notation, but what we're going to create are these new principal components. And the components, ignore the matrices for now, really it's each variable in our data set multiplied by the corresponding weight in that particular eigenvector. Right? So the first principal component, remember there were two numbers, one corresponding to SAT verbal, one corresponding to SAT math. Each of those numbers multiplied our original data. We sum them together and get our brand new Z thing, our new version. We could achieve this with the vector product of eigenvector transpose times our original data. And that's actually how it's done in the computer. That's for us doing matrix algebra based. But these weights, these regression weights, if they look like regression weights, but they're not really, they are coming from the eigenvalues of your analysis. The eigenvectors of your analysis. Eigenvectors. So, the components are formed by those weights, and they're formed in a certain manner. Right? They're not formed randomly. When it comes out of the computer, they're formed in an ordered manner, in that the first component is set to have the biggest amount of variance, meaning it has the highest eigenvalue. Right? So you find what the computer is doing, because the math doesn't care, it comes out in all sorts of ways. It goes and looks at all the eigenvalues and says, oh, this one's the biggest. So I'm going to take its eigenvector, I'm going to go and form a new component with all those eigenvector values. Eigenvector, the elements of it. And then it starts with the second one and does the same thing. Find the second largest eigenvalue, and use its eigenvector. So it's weighting them so that the variance of each component is successively smaller, right? So the biggest component has the most variance, the second biggest has the second most, and so forth. Furthermore, all of the components, these brand new variables, are completely uncorrelated. How do you like that? If this were a factor analysis, that's saying two things coming out of your head closely related enough to be on a survey are uncorrelated. That's likely to happen, right? Anyway, sorry. Not likely to happen. I don't.
Absolutely zero?
Zero.
Or like it could be close to zero?
No, enforced absolutely zero, by definition, how it comes out through math. So here is an example analysis using the correlation matrix of our original data. We have two variables here. We don't typically do this with two variables. I'll show you analysis with 10 coming up. But with two, just to kind of show you what it's doing with our variables. So we have SAT verbal on the x-axis, SAT math on the y. That's a scatter plot of our 1,000 observations. We took the correlation matrix, we put it into this code that I showed before. This is the output. Actually, I didn't show you this before. There is a procedure in R called PR comp. It's built into the R base package. That's how much use it gets. You don't have to download a package for it. It's just automatic. You tell it the data. This scale dot equals true represents telling it to go and find a correlation matrix itself. If you said this is false, it would be the covariance matrix. The reason for that is, well, we'll talk about it later. We're sticking with correlation for now. Actually, I'll talk about it now. If your variables have widely different variances, it'll show up in the component output. It'll look like one component's way more important than others because the variable that has the most variance is going to help contribute to that first eigenvalue here. itself more, disproportionately to the other variables itself. Like you get more bang for your buck with including it with a weight for it. So here, this is the analysis method, PR comp. This is the code that you'll use in your homework. The SAT PCA core, this just takes whatever it's done and outputs it, and it shows you standard deviations, and then eigenvalues, or PCs. They don't. It says rotation. We're not going to talk about that just yet. We'll get in rotation in just a moment for EFA. What this is telling us here is the standard deviation. Actually, let's look at the rotation here. PC1, those are the weights that go with the first principal component. So if we were to form a brand new principal component, we'd take negative 0.71 multiplied by SAT verbal, negative 0.71 multiplied by SAT math. We'd get our new component, and the standard deviation of that component would be 1.33. Right? So if you're thinking about this from the eigenanalysis type that I just talked about, this is the square root of the eigenvector. Right? Eigenvalue. Right? You get that eigenvalue. Eigenvalue represents the variance of this thing. The standard deviation is the square root of it. Same thing with principal component 2. Right? We could take our data and just completely form brand new components out of them altogether. Actually, people do that, used to do that. Like, everybody freaks out about multicollinearity, like way more than I think they should. If you get output if you get things that run and the standard deviation isn't 2 million, it's not multicollinearity. But when they do, a solution to it is to use principal components instead of x's. Right? If you're going to predict with these, you predict with principal components because they're uncorrelated. There's no multicollinearity. They're completely uncorrelated. Side note over. So this is your eigenvalues and eigenvectors, but not called that. Down here on the bottom in the summary is the importance of components. And it says here, it gives you again the standard deviations, and it tells you what proportion of variance each component accounts for from the total variation itself. Now, this is sort of hidden and hiding the fact that these are standard deviations, not variances. Right? If these were variances, if we took this number squared plus this number squared, we get 2 back. And it would be very easy to see that this first number is 88.7% of the value of 2. So it's sort of that hiding of things that's going on. But what we can tell with this is if we wanted to get, if we use just the first component, it would be like taking our data, being close 88% of the variation in our data altogether. So that's a pretty good approximation just with one number. If we took both, we'd get, the second component is 0.11, but you'll see the cumulative proportion right here is going up. And so when I say in homework, take the solution that has greater than 70% of variance accounted for, you're accounting for this right here, this cumulative proportion of variance. It's above 0.7, you're like, hey, I want the solution that tells me above 0.7. So that's a little weird. If we want to go and look at what this does, here's this next graph. This up here is our original data in red. KU red. Crimson. Not quite. It's R's default red. I don't think that's crimson. And over here in blue is the same data when we form principal components out of it. Right? So every person over here, every dot, they have 2 variables that go into it. I reconfigure the variables from being SAT verbal and SAT math to being component 1 and component 2 based on those eigenvector elements from the previous slide. And this is what I get out of it. That looks like our data, doesn't it? Look at what it's done. This first axis was SAT verbal. It's now principal components 1. But if you look at this data, we could just rotate it and overlay it completely, right? And that's what principal components is doing. It's essentially taking a look at our data, saying, oh, here's a scatter plot. What dimension has the most amount of variance? Well, that's like saying, if I were to draw 2 lines, how far on these data, where would they have to be to make the farthest apart and the most data in between them? So it says, oh, look, right here, this dimension right here, I'm going to call that my first principal component. And sure enough, that's what it does. Principal component 1 looks like that. has the most amount of spread. Right? Principal component 2 now is like, okay, now I need to go 90 degrees from that. Right? So here's principal component 1. I need to be orthogonal, so I'm going to come in 90 degrees from it. How much spread is left? And that's dimension 2 over here. Right, so this is me trying to show you what principal components is doing to your data. It's essentially going and saying, hey, got a lot of correlation? I'm going to give you one big component, because that correlation is the dimension that has the biggest difference. It has the variance biggest. Imagine what this would look like if we had zero correlation. Our data would be this big circular thing. Right? And if we have absolutely zero, it would be a complete circle. So anywhere you put a dimension will have the same amount of variance. Our components will be a big circle. And each component would account for essentially the same amount of variance as any one variable would happen to be. So what principal components is trying to capitalize on is that kind of shared variance that goes into multivariate data in our dimensionality that we see. Is that weird? I'm going to take a drink. Anybody think that's weird? Anybody have a shot of something I can put in here? It's okay. I'll just look away. That's how I usually give talks at conferences. No, it's not. I know, I am. Just trying to blow it all up. Just kidding. Okay. No questions. Amazing, huh? Let's talk a little bit about how we do this data. So I used to work in a lab that collected gambling data. You heard this story? You've had it before? I learned how to gamble in this lab. I learned how to gamble with grant money. And then I've been to Vegas a few times. Few times. Number of times. And yes, now I no longer gamble because I've seen the errors of my ways. And I like my money. I don't like to just, like if I were going to gamble, I'd probably just set my money on fire and at least I would get heat out of it. Right? Right? Because at least there's a little bit out of it, right? Now I gamble with things like retirement money and, dad versions of gambling. Oh yeah, I bought a hot stock this week. Anyway, I have a scale. What's that?
Oh yeah, grown-up gambling.
Sanctioned gambling. That's right. E-Trade. Anyway, this scale is based on 10 factors. So why am I doing exploratory factor analysis? Well, good question. For an example, these 10 factors come from the definition of pathological gambling from the Diagnostic and Statistical Manual of Mental Disorders, 4th edition text revision, because that was how old it was, the book that was out at the time that I did the study way back, when you guys were like in diapers. So, there were originally 41 Likert type items. There were 6 values on each that they were supposed to agree or disagree with, from strongly disagree to strongly agree. And the first time we used this was at this casino where we gambled with grant money and solicited people to come take our survey and sit in our lab and whatnot. And we'll give you $80 to go gamble. Oh, what? So we did get a few gamblers that way. Can you imagine? Our data collection would happen to be on Fridays and Saturday nights for like a month, like from like 10 p.m. till 3 a.m. Can you imagine doing data collection with that?
But you wouldn't know because there's no clocks.
There are no clocks. How we knew. We were off the boat where this happened. The other thing with it was the casino itself was very, very nice. They catered the room that we were in, and they let us take home all the food every week. And as grad students, like we were walking out with like legal boxes full of food, right? Like catered food. And someone's like, "What's in the box?" Well, oh, it's research. So it was awesome. No, it was terrible. Anyway, the point of the matter is we are going to use 1,304 subjects. And I actually have 10 items on here. I built this 10 items for an example for my structural equation modeling or confirmatory factor analysis part of my class. I teach on SEM. There are 10 items. I made the 10 so that it would fit a one-factor model. All right, so I went into it knowing I sort of whittled it down to 10 using statistics and cheating and all sorts of stuff, but I did the best I could. So we're going to do a principal components with this to show you how it works with data. to do this, you must imagine, these are all in caps because you should never do a PCA after running a CFA. They're completely different purposes. But you have to imagine these are the only 10 items that we had, and we wanted to reduce these 10 items into 1 or 2 components. Can you imagine that? Let's pretend. My kid, the 1-year-old Hugh, he's starting to pretend a little bit now. I'll put socks on my hand, make sock puppets. But for whatever reason, like talking, he thinks it's me talking because I'm a terrible voice. But I can meow like a cat. He thinks that's amazing. I can put it's like a sock puppet kitty, and oh, that's so fun. Anyway, so you got to pretend like he's pretending, right? That's a lot of disbelief here. So with this analysis, with 10 items, I have a 10 by 10 covariance or correlation matrix. I'm going to use a correlation matrix here. So the total amount of variance in that is 10. And I could come up with a total number of components equal to the number of variables, which is 10. All right? And here's what I get. These are all the standard deviations. Now remember, that is the square root of the eigenvalue. And if I wanted to cut off at 70%, look here, here's 40% cumulative, 57%, 68%, almost, but not quite. I need to go with 4 components to get at least 70% variance accounted for. So I'd pick 4. So the answer is, from those 10 items, I'm measuring 4 things about gambling. That's crazy, right? One of the things that people use to talk about how many to choose is something called a Scree Plot. Have you heard the word Scree before? What's the definition of Scree? Yeah, there you go. It's like debris at the bottom of the hill. I think you could just call it crap or a shit plot. I think that would be just, yeah, figure out where the junk is and take it there, right? It's going with the storage wars argument, right? Find someone else's junk and bid on it. Yeah, normally you look for the elbow of the plot. There's no one right way to do it. This is the Scree plot. This is the proportion of variance each eigenvalue or each component means, and this is the cumulative version of it. So you can see I was looking for 0.7, which is like right here, and that's where I get above with 4 with it. So that's the answer to question number 1. If you remember the questions. Question number 1, how many factors? How many components? Answer to number 1, 4 components. Question number 2 is, what do they mean? And this is where subjectivity comes in. All right? Here is what we call the unrotated solution. We're going to talk about rotations in just a moment, but I refuse to do it for principal components. That's an EFA type thing. You could do it in the principal component, but I'm not going to. What we need to interpret is which variables contribute most to each component. So take a look at PC1. They're all negative. It's like they're all unrelated to it. The ones that's highest, X14, but they're all in the same direction. And a lot of times in principal components analysis, the first principal component represents kind of like an overall average effect. And if you think about it, again, well, these are numbers. These are the numbers that would multiply each variable to sum them together. But they're no different than any other statistic. And what I want to say with these is, hey, wait a minute. Are they truly significantly different from 0? Does anyone ever say that? No, what they typically say is, let's look for the values bigger than 0.3. Why 0.3? Because 0.3 squared is like 10% of the variance if you round of something. Yeah, anyway. It's all layers and layers of like rules of thumb with no empirical evidence to back it up, generally speaking. It's very limited. So
it's tradition.
Tradition, that's a good way of putting it. So 0.3, 0.3, 0.3, 0.4, bigger in magnitude, negative is fine too. So we'd say, oh, item 1, 5, 13, 14, 18, and 23 all relate to PC1. So if I were to look at those items, I could say, oh yeah, that's the I hate to lose money component, because all those items may talk about money, or however, whatever feature the items happen to be there for it. Same thing with principal component 2. Now it gets harder because this X14 is strongly negative and X18 is positive. So you're saying whatever these two things are going on, it's this component strongly not 14. Item 14 was I'm drawn more by the thrill of gambling than the money I can win. And 18 is my family disapproves of me gambling. Right? So this is positively related to the component. This is negatively related to the component. What does that mean?
Reverse score.
Oh, reverse score. True. Could be. But yeah, it's all sorts of crazy with it. So, point is, whatever you do here, there's an interesting phenomenon in kind of perception. I used to be a psych person. My degree's in psych. You think about, and then decision making is part of it too. Once I show you there's 4 factors, you're going to come up with the reason why there's 4 factors. And then what you're going to do is you're going to drop anchor on that reason. There's a term for it in decision making called anchoring and adjusting. Like once you initially come up with a reason why that should be the case, it's very hard to get you to change your mind in the light of it has to take overwhelming amounts of evidence to ever change your mind from it. So I just told you there are 4 factors to my scale where I actually used another method, and I'm pretty sure there's only 1. 4. So it's an interesting phenomenon. But yeah, what do they mean? Beats me. You could spend years arguing about it and not come up with the right answer. And I will tell you statistically, what I don't like about it is I want a p-value for each of these things. I want to know which ones are significantly different from 0. Because that would help. It may be that 0.3 is a great standard, but no, we don't have enough data to say that's significantly different from 0. We really need something like 0.6. Who knows? So the final result in principal components is we have these component scores, and actually R will give it to you. You can find this out. These are the first 4 components, and these are each of the subjects of my data set, and these are their new component scores that come from the original data, multiplied by each of the elements of the eigenvectors. And so if we were to do some other analysis with principal components, we would use these and not the original data. So it'd be like saying, I'm going to go predict how often you gamble with these 4 components. And I'm going to say, hey, look at that. Principal component 1 really predicts how often you gamble. And what's the next question someone's going to ask? What is principal component 1? Oh, you know, it's like sum of item 14 and sum of item 12 and so fuzzy. Not quite the standard that we'd like to think about with data science. Benjamin.
When you have some leading questions and they're all as a theme, what's wrong with that? Like if they're all about how often do you go gamble?
That would be good, but the problem is it's subjective. Right? And so you're looking at the questions and you see them and there's a thing that's fantastic. It may completely be valid, but it's also potentially infiltrated by lots of noise in the data or in the statistics because we have no idea of the certainty of these results. They're numbers, but there's no certainty with it too, right? We can't go and say, yeah, this 0.86, yeah, that one says it's really not 14, but it's not significantly different from 0. It's like the effect size of it is next to nothing once we standardize it, right? So we shouldn't even consider 14 with that if we looked at it. Does that make it a little bit better? Other questions? Is this helpful? I'm taking most of you have seen PCA before. You've heard of eigenvalues? No. Okay, good. Some of you have, some of you haven't. We teach it in like 725 or whatever. Where have you seen it in your classes in REMS? 822 is, what's it called? Scales. Like a fish or a piano. No, neither.
Actually, it's a funny story. For 822, I did a fish scale.
Did you? That's good. I like that. That's good. Hope you got an A for that. Okay. So PCA is a data reduction technique. We still use it generally to go and take lots of data and shove it into components. It's cited as factor analysis, but really it's its own little beast. So if someone's saying factor analysis, you see eigenvalues and eigenvectors, you're kind of like, beware. It's the default option in SPSS and SAS, by the way. So if you're over there in SPSS and SAS and you're like doing factor analysis, great, you're doing principal components. Truth in advertising, right? So what is factor analysis? We're going to get there. What are the problems? What are the solvable issues with PCA? So I'm trying to be fair here, saying how can we make it work? Well, missing data is a problem. You can mention that. If you You have to listwise or pairwise delete. Now you can overcome that. We could use multiple imputation. Possible to overcome. We didn't, but we could. The distributions of the variables can be anything. There's no assumptions about the distribution of the variables in this. None whatsoever. The problem is variables with more variance contribute more to each component. So standardizing variables we could do, like the correlation matrix. But some variables can't be standardized, like gender or sex or binary things. And furthermore, like the correlation matrix doesn't even go between 0 and 1 for some things when you go away from continuous data. So all things start to get haywire. And to me, the hard part is I don't like the lack of standard errors. Now, we could do this Bootstrap approach where we resample the data. I didn't teach you that this year. I'd love to add that to this class, but I can't make it over 3 credit hours. Here we have this sample with our homework. I actually create 52 data sets in homework that are randomly drawn from the original data, 177 cases. And had I aggregated the component values, I could get a standard error around them, right? I could just come up with it. There's 52 values of each eigenvalue, and at 52 values of each eigenvector, I can give a confidence interval. I can come up with a distribution around that. I didn't, but we could. You could do that with it too. So there are ways to make this a little bit better. It's just seldom that you see that get used. So. Unsolvable issues, though, subjectivity in the process. How many components? Good guess. And what is the meaning of each component? Good guess. And so I feel like you can easily be misled by a result, or you could purposefully mislead with these analyses. So, how are we doing? How about exploratory factor analysis? Are you ready for the fun that is? Okay. Exploratory factor analysis is to determine the nature and number of latent variables, these hidden factors that account for observed variation and covariation in your data, your items, your indicators, your variables. So basically you're saying, I have all these data, if I've got 10 questions, what's the underlying thing that caused someone to respond the way they did? Right? If you go look at the homework questions, and you forgive the typos, and you see someone who, out of 10 questions, scores a 50. They're way out there on the believe every conspiracy they ever created scale. This person, if you could observe kind of the inner workings of whatever factor that happens to be, tendency to believe in conspiracies, or distrust of government, whatever you want to call it, the higher they are on that scale, that metric, the more likely they are to reply high on each of these items, right? And so that moves forward in the way that that's the definition. Sounds a lot like what people use principal components for. But remember, principal components is reducing multiple observed variables into a fewer number of components. Right? So components is necessarily taking your data already and making combinations of them with a little bit of this, a little bit of that, a little bit of this to come up with a score. Factor analysis is saying, yeah, there's something I didn't even observe in the first place, like a missing variable altogether that's doing all this. Yeah,
would PCA be used whenever you see people who revise the scale to make it smaller? Would that be like that?
Not generally, not with the modern methods. Maybe if people hadn't taken enough psychometrics, yes. The stuff that you would learn without getting to item response theory or confirmatory factor analysis classes, yes, people would use that. But generally speaking, no. There are better ways of doing it now. So I hope that helps. I won't tell you what those are. Another class. Other questions? Laughter. So methods for EFA. There are lots of methods for extraction. They all call factors things to be extracted, which sounds really terrible. Most are PCA based. Remember, that's your catch. If you see, what is it, your tell in poker, that's it. If you see an eigenvalue, that's PCA, right? All of those were developed before we had computers, right? Before we could actually go, well, computers existed, but we were in wide-scale use in science, right? So I would like to tell you today, if you're already factor analysis, ignore all of them and work with maximum likelihood. Why maximum likelihood? Right? Well, maximum likelihood gives us certain properties we like, right? It tells us, should we have a large enough sample, we get values that converge to the true numbers. We get standard errors. We get goodness of fit indices. We get all the stuff that we've used maximum likelihood for in this class, but we get it to look like the things that we just saw in principal components. So essentially it's saying we can do what they're doing, but we can do it better. The key in all of this, and the thing that I want to harp on the difference, PCA takes your existing data and recombines it to give you components. EFA, you have to go and figure out a factor through likelihood-based methods. Right? You're not taking combinations of your data. You're coming up with a statistical model for what that factor happens to be. Right? So in the EFA approach, if you wanted to come up with the factor score, you wouldn't take factor loading times variable to come up with the factor score. You would come up with a stat model, and you'd use ML in the first place to come up with that score. So, questions? It's late for me to be drinking caffeine, but I'm trying to get amped up for this big finisher. Yes, sir.
All right, so I'm having flashbacks to my undergrad days where
Easy.
EFA, well, EFA was taught in the class, but it was kind of one of these things. Like, it was taught like the way that the MMPI was first developed. Have
It's how a lot of
a
scales
ton
are.
of items, throw them out in the public, let them answer how they will, and then come back and kind of group them all together. Is that actually EFA or is that PCA?
Usually PCA.
Okay.
Absolutely. In fact, that's one of the interesting things in teaching the latent variable class I teach. People will take whatever scale they have. The BASC, who uses the BASC in here? The BASC was developed with PCA, but when you apply the factor analytics solutions to it, it doesn't fit. So then it's like, well, great. Now the modern standard doesn't fit with what we did, just 20, 30 years ago. It happens almost all the time. And it's a really interesting disconnect between methods, but I feel like the methods we're using are certainly more direct in the purpose of it. It's really tough, particularly if your advisor was someone who had developed a scale, and they did this with PCA. And then you came along and you're like, yeah, I'm using factor analysis because I want to do a structural equation model with it, and it doesn't fit. Wow, what do you do then, right? That's not a good situation, but it happens almost all the time. In fact, every time I teach a class, it seems to happen at least more than once. Okay. So in EFA, the same questions show up. We want to know how many latent factors there are now. Not components, but latent factors. They sound very similar, but they're components are recombinations of data. Latent factors are things we never could observe in the first place. Right? We're indirectly getting with data, but we can't do a recombination to get them. So how many factors do we have? And then once we figure that out, what does each factor mean? And you'll note those are the same types of questions we get from PCA, the same types of questions we get when we do a PCA analysis. We just swap out the word factor for component. And that's another similarity. I get why people are thinking they're very similar, but their approaches are different. So the factor analysis now, this looks a whole lot like the EFA from before, or the PCA from before, but it's really not. Each item that we've collected for each person, we're going to go and use a linear regression for. We're going to predict it with some item intercept and some series of factors that are multiplied by regression weights that we call factor loadings. All right? And there's a set of error that shows up at the end. So basically what we're doing is, had we observed these latent factors, had we had those data, we're essentially saying we're going to go and see how well those factors describe why people are responding the way they are on each of the items. And from that, we can disentangle how much was due to the factor and how much was due to idiosyncratic properties of each item with respect to residual variance for each item. Okay. So all that's crazy. You can do it in matrices if you want. In maximum likelihood, the thing I didn't say from the other slide, believe it or not, this down here, the maximum likelihood function has to have a likelihood function to do this. The likelihood function is based on multivariate normal, which is the same likelihood function that we started with in class this year. Actually, we started with univariate. But the thing that we work with in Levon, multivariate normal. The thing that we work with in GLS, multivariate normal. That is the same likelihood function that you've been working with in all these other cases. It's the same stuff. So now trying to bring back what you've learned already to put this into context. Using that likelihood is very familiar. Furthermore, the likelihood function is identical should you be using the EFA version of it compared to the confirmatory factor analysis version of it. So now, if you're in the ML world, it's the same likelihood function. The only thing that can differ are the set of model constraints you put in, like what we're talking about in the previous class between unstructured covariance matrices and compound symmetric versions of them, or something in an analogous sense. Right? So when you start to say, I'm going to do maximum likelihood for it, you're almost in the confirmatory world already. In fact, you're using the same likelihood as confirmatory factor analysis uses. So if you're going to give me maximum likelihood, I'm going to say, if you're going to do exploratory, do it the confirmatory way. But I digress. So how it works, we have this multivariate normal distribution, and it depends on the covariance matrix and the mean vector. There's all sorts of solution, but this is all the matrices that go behind it. You don't need that for today. What I want to tell you, how do you figure out how many factors you can have? Do you remember in path analysis we had to figure out if the model was over-identified, under-identified, or just identified? Same thing happens in EFA with maximum likelihood. We don't get eigenvalues and eigenvectors out of it. What we get is our covariance matrix recombined into a set of key terms, factor loadings, and residual variances, which we call unique variances. So the way that we tell how many parameters we can estimate is by coming up with a count of the total number of parameters that would be in a saturated covariance matrix already, just like we did in path analysis. Right? So if we had 2 items, like the SAT math, SAT verbal, there would be 3 unique parameters. If we had 10 items, the number of unique parameters in that covariance matrix, there are 10 variances, and there's 10 choose 2 off-diagonal covariances, for I think a total of 55 parameters. Well, each time we go about getting a factor, every item gets a loading. So the first factor would have 10 factor loadings, and there's always a unique variance or a variance of error for each item. So the first factor would have 20 total parameters. The second factor would have another 10. But when you have another factor, we have to start putting constraints in, because there was another rule in path analysis that causes things to go haywire. So it's like saying, oh, I'm going to add another 10 parameters, but it's actually 10 minus 1, or 9. So the way that you can determine it is you have to figure out, for an analysis with F factors and capital I items, there are this many model parameters. And what we're going to see is this is the total possible parameters, but we have to put in a set of constraints to make it identified. Right? It's not just, there were 2 identification criteria in path analysis. There was the count, the global, and then there was the local. This is the latter, the local, to make it work, to uniquely identify it. And this is where EFA with ML falls off the rails. We have to do this additional step to figure out how to identify our parameters. So what you'll see, I'm interpreting this slide, it's going to be relevant in homework, although you can probably map this example in homework. You have 10 items. You'll have 10 times 11 over 2, or 55 total parameters. You plug in F over on this side, right? For one factor, you get 10 times 2, which is 20, minus 0, 20. So 20 is less than 55. If you have 2 factors, you get 10 times 3, it's 30, minus 2 over 2 with minus 1 is 29. Right? So you keep moving up, and at some point, the number of total parameters, which is EFA ones minus constraints, will equal the number of parameters you have in your covariance matrix. That is when you have a solution that's equal to the saturated model. That's what we saw before. That's all the analyses we started with, right? With the unstructured models, we have the saturated model show up. So what we end up with is, in thinking about this from a factor analytic or a path analytic framework, we go and say, okay, I have a factor solution. If the factor solution fits the data, it should represent my covariance matrix, the unstructured version of my covariance matrix, within reason, within good model fit, right? And just like we saw, do you remember the model fit indices in path analysis? We had the likelihood ratio test. We had RMSEA, the root mean squared. Want that low CFI and TLI high. We can use those in the analysis if it were CFA. If we do this the right way. So we have a different standard for fit. Going quick. Where am I going with this? When you look at this with parameters, with the way this differs from PCA, in PCA you're expecting to see eigenvalues and eigenvectors, and one per variable. In the EFA analog to it, you will not have eigenvalues, you will not have eigenvectors, and furthermore, you can't have one factor per variable. In fact, the maximum number is going to be far less than the number of variables you have. But that's okay. It's seldom the case where you're going to take a 10 variable data set and come back with 10 principal components. That would be a very bad idea. Just use the 10 variables in the first place, right? So in maximum likelihood factor analysis, the game is a little bit different than what you see people talking about. But that's okay, because I think it's a better way of doing things. So what are these additional constraints? This f times f minus 1 over 2 constraints to make our model work, to solve the identification condition. And this is the thing that very, very few user guides tell you anything about. They're the following. If you take your vector or matrix of factor loadings, right? So if you took all the loadings from here and put them into a matrix, right? So you'd have items by factors, that's the size of it. And then you took all the residual variances and put it into a diagonal matrix that was square, so it would be the number of items in distance. If you did all that, then if you created a product of factor loading transpose, so in this case, let's imagine we have two factors. Right? This would be 10 by 2. The transpose of it is 2 by 10 times a 10 by 10 times a 10 by 2 gives us a 2 by 2 result. That 2 by 2 result, it's called delta in the language for it, has to be diagonal. What? That's the constraint. That's crazy. Who wants to volunteer what that means? Because you can come up and teach the class. I can't tell you what that means. But that is a statistical constraint. Just like we would impose compound symmetry, just like we would impose sphericity, just like what we saw in the last class, we had compound symmetry heterogeneous. That's a constraint. This is a constraint. Right? And like any other model that you see in this class, putting constraints on the data, we should know what they happen to do. And so when we get there, when we get to CFA version of this, we're going to put the same number of constraints in. It's just we're going to know what they mean. It's not going to be this crazy set of constraints that we see here. Right? So what does it mean? Here's a two-factor model. It means that across all the items, the sum of the product of the items' residual variance times their product of loading should be equal to 0. It imposes that as a constraint. It just makes that to be the case. That's nuts. If you have an item that that doesn't fit this, too bad. Probably going to extract another factor. That's usually what happens. Right? Good luck. It's a crazy constraint. Has anyone ever seen this before? Those of you who've taken factor analysis and heard about maximum likelihood, have you seen the constraints that go with it? That's it. Right there. That's the problem. That's why I hate it. Right there. I actually had one of my colleagues come in my office and like, you can't say you hate it. I'm like, I drew this equation up there on my whiteboard for them, this person. I'm like, that's why I hate it. I can tell you right there, that's it right there. That is a set of constraints that nobody understands. It's crazy. Why would you do it? Instead, put in constraints that you know. Then you can solve this problem. But nobody even talks about it. It's not even brought up. Or even just getting the fact that maximum likelihood versions exist that don't give you eigenvalues and eigenvectors is a big hurdle for a lot of people. So, anyway. Questions? I need a drink. We all need a drink. Okay. So, what we can do in all of this, if we're talking about likelihood function, this is the likelihood function expressed with our model parameters. We can build a likelihood function. But let's talk a little bit about how it works. We're going to build, R has a function to do MLEFA. It's called factinal. That's the name of it. It's bad. And yes, I saw the spelling of that, and I thought that's unfortunate. Or maybe that fits with the way the class happens. We are going to use factinal, but what you'll notice is that factinal, in spite of using maximum likelihood, still insists that you have complete data. If you don't, too bad. This is very bad. But I threw out all the data. By the way, your homework data is complete. You don't need to manipulate it in any way, shape, or form to do the analyses. I'm trying to help you out here, right? So don't worry about that. So, how do we make this work? We first have to determine the number of factors we have. How do we do that? Ooh, good question. We actually can't just run factinal one time. We have to run it multiple times, right? So we will run it. Here's the factinal syntax. We tell it our data. We tell it the number of factors we want. We tell it which rotation we want. Rotations we'll talk about in just a little bit. For this case, we just want none. It doesn't matter. The fit with rotations usually is the same, should be the same, regardless. I'll tell you what those are in just a bit. Here's our output. We get uniquenesses. This is another term for residual variance. So this is remember, each item has its own regression line now. So each item gets its own residual variance. That's variance attributed to the item. In the world of CFA, we call that's the measurement error right there. That's the stuff that's not explained by the trait that's underlying the test. The factor loadings show up. These look a whole lot like those eigenvalues, or those eigenvector elements, but don't confuse them with it. We don't use these to multiply our data to come up with a component. These are the regression weights that multiply this hypothetical factor that we didn't observe. So if we're interpreting this output, it's like saying, hey, look at that. This factor that represents gambling, okay, item 9 has a regression slope of 0.76. Item 14 has a regression slope of 0.378. But we never got the actual term itself. Do you see the distinction? So, but the key in all of this is at the bottom. It gives you this junk about sum of squared loadings. Ignore it. Doesn't matter. This has nothing to do with what we want. What we want is right here. Is one factor enough? It says the test of hypothesis is that one factor is significant. The chi-square statistic is 161.14 on 35 degrees of freedom. The p-value is very small. Wouldn't you know it? That's the comparison, the likelihood ratio test of this model versus the saturated model. So the likelihood ratio test is testing, this is essentially our null hypothesis that one factor fits the data. Saturated model is the alternative. Everything fits into it. So we can always compare it. And we reject the null hypothesis that the one factor fits the data. And we now have to move forward. I did ask this as a comps question in the oral. How would you determine the number of factors if you didn't have eigenvalues and eigenvectors? For those of you who are in comps. Anyway. So I can do this with multiple fits. So if I wanted to test the number of factors I had, I could just do multiple analyses where I change factors equals 1 to factors equals 2, factors equals 3, and so forth. And this is what I get out of it. P-value very small, still significant, and voila, 4 factors seems to fit. And sure enough, this happens to match the 4 components from before, but that's likely by chance. By the way, those constraints I talked about, this is just an example of it. If I can do the matrix algebra, you'll see the diagonal of this is a number that's not 0. The off diagonal is either 0 exactly or some very small number very close to 0, showing that the constraints, this is what's making the parameters work. But that said, here are the factor loadings. What does that mean? R does me a solid and drops some factor loadings from this. I don't know which ones. I really don't care. I don't want to interpret these. But now I could go interpret these factors. And again, all the factor loadings on the first factor show up. Like an overall average gambling tendency, if you want to call it that. But let's hold off on interpretation because there's a better way. What people used to do with factor loadings, if you're doing this and trying to estimate every single one subject to these constraints, you could use something called a rotation, which is you don't like the solution that R gives you? That's fine. Rotate it. Spin it around. Find a solution that's more interpretable. Then publish it. Because it's not just subjective to figure out what it means, it's subjective to figure out how to rotate it. Turns out, the matrix of factor loadings, this thing, if you've estimated every one of them, it's easy to go and flip the meanings of them mathematically. In fact, if you multiply that matrix by some other rotation matrix, you can come up with a result that is the same statistically, like the likelihood would be the same, but the different configurations of where the loadings are big and small. And that's what a rotation happens to be. There are two types of rotations that generally get talked about. There are orthogonal rotations. One of these is called Variances. There are oblique rotations. Orthogonal meaning, by the way, no correlation between the factors. Oblique meaning correlation allowed somehow through matrices. There's the math behind it. It's telling you it works. There are newer versions of rotations. And I would say new as in like 30 years old. There's an article by Michael Brown in 2001 that talks about different methods. M+ popularizes one geomin method. The reason why it popularized it was because, if you guys remember this from SEM, one book chapter, not peer-reviewed, had a simulation study where it took one data set from Thurstone and it worked better. So therefore it is popular. Subjectivity to the rescue. So for instance, this is the Varimax rotation. So if I switch out rotation equals none to rotation equals Varimax, this is what I get. What it's supposed to do is push some of the loadings bigger in some directions and some smaller, and this really just makes it harder to interpret. This one, this is the Promax rotation. It gives me a factor loading bigger than one that says, so there's something else wrong with our analysis. But point is, if you're interpreting these things, stop. I'm just going through this quick because this is how people like to do this. They even use rotations in PCA. Stop it. If you want to do this, do it the CFA way. All right? I'll show you that right here. EFA via CFA. Finally, the big crescendo. Because the likelihoods are the same between EFA and CFA, and the confirmatory analysis allows us to really go and specify what a factor should mean, we can trick the confirmatory analysis into doing EFA for us by setting constraints that are a little bit better. This is sort of talked about in other places. There's a factor analysis book, it's now in its third edition, second edition by Brown in 2002, that talks a little bit about this. But what I mean by constraints, it's this. If we are looking at our solution here, we're estimating every one of the factor loadings for every factor. But ultimately, what we're trying to come up with is a description that says, hey, yeah, factor 2, this item, and this item are the three that drive it. Everything else is effectively 0. CFA likes to go in and put those zeros in place and not estimate the loadings. And that's where it gets its name confirmatory. It says, oh, you think these 3 items define this factor? Cool, we'll estimate those loadings for those. We'll keep the other ones at 0. They won't impact the factor directly at all. You're fine. So what we can do with CFA is come up with a set of constraints that's the minimum number. And we'll get the same fit as what the EFA and ML work, but we'll get all the CFA benefits like the model fit indices, the standard errors, the lack of needing a rotation. All of that gets locked in with it. So how do we do it? We have to go and fix the factor loadings to something called row echelon form. This is a nod to one of my former advisors. Basically this, if you have one factor, there are no constraints on the loadings. If you're estimating a model with 2, you have to take one item and put a 0 in for one of its loadings. It's like saying, yeah, this item, it doesn't load on factor 2. Well, that should be okay because you generally want an item only to load on one factor, right? So it doesn't matter if it's factor 2 won't really make a difference which one you pick. It's just like, oh yeah, that one doesn't be on that one. So whatever that item should have loaded on, it will load on the first factor, and that will be the first factor. Factor 2 won't include it. Right? If you have 3 factors, then you'll have to go and take 2 items and have them not load on one of the factors. For 2 items, they get zeros on one of the factors. And for one of those items, they get a 0 on the other one. And I'll show you how this shows up. So, sure enough, we're going to use the package we used for path analysis to this. Remember Lavon? Do you love Lavon? It's almost like, if I were to call it Lavon, it would be with an O. L-O-V-E. Love. Love on, right? That's it. Because that's how, no, I wouldn't say that. It's terrible. It's late. I have been drinking. Coke Zero.
Yep, sure.
Strong drink. So how we do this is to define a factor that looks like a regression. In your path analysis, you said outcome or dependent variable equals, and you did its predictors. To make a factor, you do equal tilde. Clunky notation, clunky direction, because each of these is really the dependent variable. Each of the variables are dependent here, and the factor is the independent variable. But this is saying I'm going to estimate a factor model where factor 1 is estimated. That's the factor. And there are 10 items, and all of them load onto this factor. All right? And so we can use Lavon syntax. I switched this up to say CFA. We could have used SEM from before. They're all the same. We're going to use the MLR estimator. Remember MLR, robust maximum likelihood, helped when you had platykurtic or leptokurtic data, helped those standard errors. We're going to get standard errors. And here's what we get. Ooh, small font. You're following along on your paper, because I can't zoom in on this very easily. Actually, I probably can. Okay, so again, we get all our model fit output. Remember that model fit information we got before? Remember how fun that was? We get our likelihood ratio test. This tells us what we already knew from the EFA, which doesn't fit the saturated model. But we can go look at the RMSEA, for instance. The RMSEA on this one is off the screen. 0.038. Boom. You see an RMSEA like that, and you're done. That's a one-factor analysis model, right? That's good. That seems somewhat subjective, doesn't it? But yes, it's better approximate measures of fit. CFI and TLI are also good. Generally speaking, that likelihood ratio test does not work well in these situations for varying reasons. We also get our factor loadings. Here for the one factor. We get our item means, that's the model parameter. We get our residual variances. This is the squared term of the uniquenesses from the previous slide. And if I move forward one slide, take a look at this. Here's the EFA from Factinal. These factor loadings are identical to the standardized factor loadings over here. Here are the factor loadings of standardized.all. 0.569, 0.521. If I flip back to the previous slide, 0.569, 0.521. We are doing the same thing. It's the same likelihood function. If we go a step further, take a look at this chi-square statistic. 161.14 on 35 degrees of freedom. Go back a slide. The rounding is off on this, and I can't tell which function's off, but 161.84 is the ML solution. That's the close one on 35 degrees of freedom. So what I'm trying to get you to think here is if you're going to do EFA and you're going to do ML, the likelihood function is the same as if you do CFA with it. We didn't have to put constraints to one factor. What do you think? This is the crescendo. If we go with one factor, we don't need constraints because there's only one. With two factors, though, that's where we need constraints. And so here come the constraints. We have to go and specify factor 1 and factor 2. And arbitrarily, I said, oh, item 1 isn't going to load on factor 2. Just going to leave it as is. Right? So now what I've done is I've locked in my rotation. I'm saying whatever the solution is, factor 2 is the factor where item 1 doesn't apply. Just lock that in. That's the one constraint. That would be like that sum of the squared loadings with the unique variances from the EFA and factinal. It's doing that, but it's not doing it in this form. So I'm saying that one should be 0, calling it good. I also have to go and set the covariance between these factors to 0. Now, it's funny, Levon will actually estimate it with it being non-zero, but it shouldn't. It's an unidentified model, so don't do that. But here it comes. Now, I get model fit again. Now, this ML result is going to be what factinal gave me. But the robust ML is different, and actually the robust ML is almost not significantly different. So this is almost a preferred solution. And my result, if this were my final result, if I'm saying, yeah, that's close enough, I'm going to call this good, then I would say, okay, here's my factor 1. All the loadings are positive, they're all significant. It's like saying this is our overall gambling factor or something like that. Take a look at factor 2. Here are my loadings. I don't want to look at the strength of the loadings or the strength of the standardized loading. I can tell whether or not from this wald test whether or not they're significantly different from 0. Right? Most are not. So let's keep this going for a little bit. I've got a couple minutes left. Here's the 3-factor model. Here's the 4. Oops. I'll just stop there. 4 actually broke. 4 didn't run. Different estimator. So let's imagine, okay, 3-factor model. We're happy with this fit. Here's a solution that can happen in the CFA approach that totally tells me that what we're doing in EFA is messed up. Right? So the 3-factor model. Look at that. It's amazing. It fits, we pretend. So let's go interpret our factors. Factor 1, all positive, all significantly different from 0. Factor 2, wait a minute. None of my factor loadings are significantly different from 0. In fact, when I look at that, if I were to go with that with any of those regression lines, it's like saying the slope of all these items that multiplies factor 2, they're all effectively 0. Or another way of putting that is that factor 2 doesn't apply to any of these items. So put into terms that are better, we don't need factor 2 because it doesn't significantly predict item responses. Even though this model fits slightly better, it doesn't tell us anything. Whoa. Same thing with factor 3. Look at those p-values. Those p-values are all non-significant. So even if we thought, hey, yeah, the 3-factor model is what I want, interpreting these factors would lead you to a 1-factor solution, which is where we started with these data in the first place. Whew. Yes, the thing.
So going back with the 2-factor model, how some of the items were significant, whereas all the ones on factor 1, how do you kind of deal with that when you have like 1.5?
Well, that's the hard part. There are a minimum number of items you need to identify it. What I would do, if this were your final model and you were down with that being it, I'd go back and I'd take out the items that were just non-significant. Just like in path analysis, when we had paths that were non-significant, we'd take them out. Take those out. Take those loadings. Fix all these loadings to 0. It should not make the fit much worse. And then you lock in the fact that this factor represents these 4 items, and you still have to interpret it that way. I don't like interpreting it that way, but if you have to do an exploratory approach, do it this way. That's what I'm saying. So you're still back to having to do, I don't know, but you have it, I feel like, with better numbers. What else? So in your homework, we wrap this up. Here's your last question. As this is the last question of this class, I am happy. Anyway, I am asking you to do the following. Principal components using the PR comp. Figure out how many components, how many total you need, how many components in your data set show up. What's the largest component, SD? It's just right from the output. And tell me the eigenvector, the element of the eigenvector for item 1 and component 1. I know all of you have one of those, right? Each of you is going to have a different number of components that comes out. The other thing, then I'm going to ask you to flip to the ML version of it. And I'm asking you to do each of these versions because even though I prefer you to do CFA, and in fact, if you come work with me on anything, like a lot of times people come back, like, I've done this at EFA. It's not CFA, I'm not talking to you, right? I'm not going to do it. Want you to do this because sometimes some advisor or somebody, outside member of your committee will insist. Same thing with the fact anal function. At the very end of it, I ask you to rotate things. What I'm hoping you're doing, even though there are probably somewhere between, there are 15 total questions. You may have to run 13 models to get the answers to all of them, but the lines of syntax should be relatively small for those, except for when you get to the Levon part. I don't like using an RMSEA of 0.11 to make this work, but that's to make it work with these data and this homework assignment. So everybody would have a solution that wasn't 6 factors. What else? So that's homework, 2 weeks for it. With everything we've learned in the lecture today, you should be able to go back to it, follow along. When you're looking at this, what I ask you to do, just for your knowledge, if you're learning this, you can answer the questions very quick, but be asking yourself, what does this mean? You've got the items there. Try to come up with an interpretation for each of those factors, right? And then realize that if you have a friend in the class and you came up with, if the PC analysis for you came up with 4 factors and then EFA had 2 and CFA had 1, your friend might have the reverse, 1, 4, and 6, something along those lines, right? So realize that as you're going forward too, but just try to look at the analysis, try to look at the factor loadings, try to look at the eigenvalues and eigenvectors, and try to interpret what each of those components or factors mean as you're going. That's where I am not the computer scientist that can build this section. The results section would be, we found 4 factors, and here are what the 4 factors mean. These items load on this, and these items load. I can't code all that. I can't get that to work for each of you, so I couldn't give you a test of that. But in your mind, as you're looking at it, just take a look at it if you're interested in learning this. Okay, so on that, I have a minute. Any questions? We're done. Good night. Have a good week. I will have a new lecture next week. It'll all be on clustering.